I did use that. I did it too.
All right, welcome everyone. All right, questions from last time or general questions? Any questions? Okay, Brittany, do you mind introducing yourself? All right. Yeah, so Brittany has also been the TA in labs. So if you have lab questions or material content questions, she's great with either of those. So feel free to drop into her office hours, or for either any of the TAs, you are welcome to schedule one-on-one appointments if their office hours doesn't work for you. So use them as a resource. They have the time and availability. So set those up if you want one-on-one. Feel free to reach out to whoever you're comfortable with. And then also, if you have any grading questions, so I had one student already complete the homework that's due tomorrow. And on it, it said like 0.0025, and he put in like 0.0024. And so if you have something like that and the auto grading isn't actually grading it kind of close enough, just send Brittany an email and let her know that I actually did this. Can you just mark it correct? So, all right. All right. Thank you. All right. Any questions? Any comments? So announcements. Tomorrow is your first homework. Your discussion is also due tomorrow. And then Friday will be your first quiz. The quiz will be similar to the homeworks where you have an RC circuit and an RL circuit, and it will ask you to solve those. So that will be what the quiz will be. Okay, hopefully straightforward. The next quiz will be on this RLC that we're working on. So just so you know where we're kind of going from here. All right. The other thing that I wanted to share is, so I'm doing things a little differently today. So I'm actually streaming through Zoom. So if it gets delayed, kind of let me know, because I may not notice it as much as you guys. So if it's annoying, then I'll hook it back up through the wire. But I was trying to do it more. Oh, that's great. There we go. Wirelessly if possible, since I don't have a wire stuck to me as I'm moving around. All right. The other thing that I wanted to bring up, again, like on the campus, on the Canvas page, is the handouts and lectures. So I forgot to post Monday. So sometimes I'll forget. If you're like, oh, I need to see these tomorrow, just send me an email and be like, can you post those? Otherwise, I sometimes won't remember till Thursday. And so I'll get those, or Wednesday night, try and get them done all by Wednesday night, at least, to help with the homework if you needed to see those. But if I forget, just note that you can ping me and I'll try and get those uploaded. So this is going to be the location of all the handouts that we do in here. If you want to download them beforehand to have them so you don't have to draw out all the circuits, feel free to do that. The other, oh, I don't know if I put it on here. Okay, no, I didn't put it on the learning materials. So underneath the learning materials, there's this Unit 1 practice problems. These are going to be the ones that you can do just to get extra practice beyond the homework. So I have a big database of homework problems. And so every time you do the homework, hopefully you're getting a new problem. It's supposed to generate a new problem each time. And then the Unit 1 practice problems are also drawing from that database. So some of them may be some that you've seen from the homework, but they'll again should be probably a new problem. And it will help you to prepare for the actual exam. So on these, you'll notice like this one will be an RC circuit. Here's an RL. Here's an RLC. And RLC circuits on there. So this is going to be basically what we're going to have for the first exam. So these will be practice problems that will be similar to the exam. So we haven't gone over all the material for the RLC yet, but you can do and use, even if you want to try some of them and just use them as practice, just note that they're there. And they are drawing from a large database. So hopefully they should be pretty much new problems. I still haven't been able to get to like creating all the solutions yet. But at least with the values, you'll know if you're right or wrong. So that can give you an indication. If you have any questions until I get all of the solutions posted, just reach out to me, or you can work through some of these problems with either Brittany or Katie or Sean. So, all right, great resource. Just want to make sure everybody is aware of those. All right, any questions about where content is, where to find some practices? Okay, let's get back to RLC. So RLC, what was the procedure to solve these circuits? Oh, let me back up for 1 second. I had a student kind of comment, do I have to know how to derive this from scratch every time? So no. No, what I'm going to focus on is the application. So the derivation helps you understand like, oh, well, this would be an end circuit. So that's why I need to use the final circuit to find that value within the solution. So that's what I want you to take away from the derivation. I won't require you to rederive this on an exam, I'm going to give you more of the problem and say, I want you to actually solve these for values. Like derive or solve the equation. So understanding how to use this table is going to be very helpful. So we will go over more and more problems like this. So what did we do in this circuit to solve this? Summary of the quick steps.
I believe you start by finding out whether or not the RLC circuit is in series or parallel.
Correct.
After that, you would calculate alpha and omega naught, and then compare the two to see if it's overdamped, critically damped, or underdamped, and then use the table.
Good summary. Thank you. Okay, so that was a very good summary for those online that may not have heard all of that. One, figure out series or parallel connection for the circuit. From there, alpha and omega calculation, compare the two, then use the table and plug in the values from there. So sounds really simple, right? All right, so a few little tricks to it. The last time we solved this one, and did we finish all the notes on these? Two. So we did solve this one too, didn't we? 10 millifarad. Okay, so we might be at the next lecture notes. All right, so we're on this one. Okay. All right, so why don't we go ahead? You guys can break up into small groups and work on trying to solve this one. All right, quick question again. How do you find RTH for the alpha? What circuit position are you finding it in? Okay, good. Okay, so final position is the one where you find for the alpha, because again, you're trying to find initial and value, and then everything in between is determined by, is it overdamped, underdamped, or critically damped? So that final circuit. All right, I encourage you guys online to kind of work as a group. You guys are welcome to annotate, quite a few of you guys online. Actually, let me make you guys in some breakout rooms. So if you want to take a screenshot of this, and then in the breakout rooms, you guys can annotate it together. I will move you guys into some rooms since there's such a large group here today. Maybe. Okay, I'll let you guys choose rooms if you do want to switch rooms, because there's some people. Oh, okay. That's good to know that there's a train delay. I was like, wow, there's a lot of people on here today. So I'll create 2 rooms. If you guys want to swap between the rooms, feel free. Maybe. There we go. Okay. So I'll assign you initially, and then again, just swap around if you want to.
I think it's.
Yes, everything is fine.
Yeah, no, just like trying to figure out how to move. Get back to the other room. Okay. Okay, I'm back. I think I got this.
Otherwise, yeah. Well, he couldn't remember it. It is something.
Circuit configuration do you use to determine is it in parallel spirit? Yeah. You got to find it all. So also the final for the configuration. Okay. So question came up also about like, okay, well, if this is what it is, then I have now a component in between these if they're in series. So how do I do that? So you can move elements around when they're in series. Yep. So if I have this, the current going through them is the same as if I had this, right? Voltages on the ends are going to be the same. The distribution of the voltages across them will be different. But the addition across the whole thing would be the same. So you can move elements around on a wire just like that. That makes sense?
Thank you.
Okay.
You don't need to, whenever you need to root them, you just flies in the past. Yeah, yeah.
It's like zero money.
Yeah. That's looking like the solution
Yeah.
Yeah.
So S1 and S2 are calculated with alpha and omega, which uses that R. And that's where it comes in. So you have to copy down the S1 and S2 also. Yep, they're on that graph or on the table too. And oh, that's
Like the bin was like,
yeah.
But still we.
No. What we're going to do, we're going to get the second. Find their roots. And those will be multiplied by. Which, yeah. This by itself, and then it will also be done by itself.
Yeah, but you can't supply it. Oh, I was assuming it was like that. That's why I was like. The way that capacitor, that resistor isn't parallel, so we can sort of transform that. And then we can do a.
The way they sort me. Basically, that's the name. Well, Right here, aren't these the, characters of second order? And they're of that form of unit that has if it's alpha minus omega, positive right here. Okay, okay, that's why other forms of the side. Alright. Yeah, okay, I remember. That's under there because you have that this line is this turns into a negative. It's gonna turn out to be like something right. And the way to like turn that into like different
We would ignore that.
it's like it's like
We have to use the. Our dad.
like calculate the smaller one of these. Like, I have the bigger thing. But like, I was kind of one very small. Like the annoying things, like, I just want to like smile. Against that. Honestly, it's that the Microsoft slide would be
Negative.
Yeah. When we're trying to find. Is that 0 minus?
I'm pretty sure it's 0 minus, but let me just make sure. Zero. Ooh, it is at T equals 0 plus. It's actually at 0 plus.
Sort of the IC and ECE. Yeah.
So Katie and Brittany, I told you guys wrong as far as like that initial value. You do have to find it at 0 plus. So they do have to put in the sources to find the 0 plus. I see 0, 0.
Because you remember that we know. Yeah. Oh.
Okay, I think we're all back now. Okay, so first thing to do is to find, is it in series or parallel? Again, look at the final circuit to determine that. And so the final circuit looks like this. And so hopefully you can see that they're in series for the connection. So that's the first step, is to determine series or parallel. So in this case, it's in series. From there, you have to find alpha and omega naught. Alpha is going to be RTH over 2L for a series connection. And omega naught is the same. So 1 over square root of LC, or square root of 1 over LC. Again, in the final position, you can move the elements. So if I wanted to move the inductor and swap it in the same into the location where the capacitor is, I can do that and then move over so I can combine these together. And then from there, I can take the AB across them to find the RTH. So you can visually see it, or you can physically move it, redraw the circuit with them moved, and then look at the RTH from there. So for RTH, this becomes an open. And so my pathway between A to B is going to be, well, there was another wire here, or resistor here. What was that one? 0.1. So my pathway through here, I go through the 0.52 and then I go through the 0.1. What happens once I come to this point? What's going on with that 0.1 resistance? Right? It's just dangling on another wire. So it doesn't have any connection to your L or C. So you ignore it. And then you get back to the other side. So RTH is 0.52 plus 0.1 for 0.62. Do you guys see why you ignore the 0.1? Some of you, yes. Some of you probably like, no. Okay, more nesses. Okay, good. All right, so 0.62 will be the value for alpha, or for RTH of alpha. And L is 0.05. So I get a value of 6.2. And omega naught, I get a value of 0.005 times 1 over 1.8, which gives me a value of 6. So I have that alpha is greater than omega naught. So I get overdamped. So I use this equation set, and I notice in here that there's this S1 and S2. So I need to also grab the equations for those, which are located at the bottom of the relationships there. So now the question comes up of finding these values. So I see I need an initial value for IC, an initial value for VC, and then a final value for VC. We're talking about finding the voltage. So remember, this is the voltage across the capacitor here. So we know that the voltage cannot change for a capacitance. So that is, again, a characteristic you have to understand. Voltage can't change. Current, though, can change instantaneously across it. So your current draw could actually be different right before the switch and right after the switch. So the initial conditions for IC0 and VC0, and really any time you're trying to find that initial condition, it's right after the switch has occurred at like that 0+ time. So I have to find two circuits for initial conditions. In this case, in the other cases we've looked at so far, it's been the same between when the circuit was switched and after it. And so those values didn't change. This is a condition where they do change. And so 0-, you're going to, this one. So figuring out what's going on with the capacitor and the inductor. So this becomes just a wire. And your capacitor acts as an open. And then the switch was closed. So we need to analyze this circuit. What do we notice right away? What's the current here? 0. And so my voltage that I'm trying to find for my capacitor is going to be at that node there. I can call it, I'll just call it VC. I don't have a ground here, so what do I do? Where? Okay. So I can put a ground here. You guys know what I'm going to do next? Node voltage. Okay. So I have a -4 milli coming in. And then it will be VC -0 over 0.1. What's the current in this branch? So that's what, those were those two. And then this branch here with the
EC over 0.1.
and then another VC 0.1. So I can solve this and get a VC of 0.2 milli. And this is kind of at 0-. For this initial time, I also need IL. So how do I find IL minus?
Yes.
So IC is going to be different than IL. Do you see that?
Question.
Yes.
We need IL.
To find the next step.
Makes-
You'll see in a second why. Yes.
So when we determine that there's no current going, because there's an open over those 2 points.
Uh-huh.
You choose to go pick the VC node where it is.
So if there's no current there, what that resistor doesn't have any effect. It looks just like a wire, right? There's no voltage. Zero current, there's zero voltage. So if I was to kind of color code these to my bright pink, this is all of the same wire.
So it's in parallel, so like,
Point one is in parallel with point one is in parallel with 4 milli. And you're trying to find the VC across each of those each of those parallel forms. Does that visually see it now?
yes,
Okay.
we could current do it, by the way, if you find that out.
Uh-huh. Again, lots of mistakes made at
Yeah,
that point.
or no,
Or node voltage. So what you need to notice here is where is that IL minus 0 minus current going? It's going, find another color. It's going down here too, right? And I've described that already in my node voltage equation.
yes, it's,
So that's just going to be VC over 0.1. Which gives me 0.2 milli over 0.1. Which gives me 2 milli. And the reason I have to do this step is because I know the current can't change. Across the inductor. So I use those two properties to then find the actual initial condition, which is at 0 plus. So we use that time frame. And this way I had the current going in this direction. It's 2 milli. And then I replace the voltage with this initial value of 0.2 millivolts. And after the switch, this position is open. So this is where I'm going to actually find this IC0.
is a 0 plus.
Is at 0 plus. And there is going to be current there. What is that current going to be?
IL.
2 milli. Correct. So this is the value I actually am going to use for that initial value of IC0. What is the initial value of VC0 going to be?
When we look at the initial for VC0, is that 0 plus or 0 minus? Or what is it?
It's actually always 0 plus, but they're the same, right? So this is 0.2 milli. So there's my initial value for that one. Yes.
What cases, when we, like, what kind of problems, will we have like one initial state and like, you know, just T0 minus, and when will we have initial states that also include T0 plus?
So it's always good practice to look at that. Like doing it always is going to be good practice because that will always give you the correct one. What you'll start to notice is like, oh, well, if I'm finding the voltage and I find it at 0 minus, it's the same. And so I don't have to do that extra step. But otherwise, always do the extra step. Yes.
So IL0 minus is just gonna be like we pretend there's a current going through that open circuit on T equals 0 plus.
Oops. I don't know if I know what you're asking. So this is 0 minus here. It goes through this wire and then goes downward because there's no current here.
But then at T equals 0 plus for the inductor,
Uh-huh.
I'm just put an open circuit. Doesn't that mean there's no like current going through that?
So here there's no current. So it doesn't go down the open circuit branch. So it's all got to go in this direction.
I think he's talking about where the inductor is.
So the inductor gets replaced right as it switches, which is 0 plus, to a current source. And then over time, it becomes a wire.
But can't change instantaneously.
It cannot change instantaneously. That makes sense?
So, five, two, six, then effect.
It doesn't because the current from the inductor forces it to be that value in the branch. But if the inductor is in a different location, you could possibly have different current based on the source. That the 0.52 would affect it. Yes.
Following up to my question about T0 minus and T0 plus.
Uh-huh.
Were you saying that voltage will be the same across T0 minus and T0 plus, but rates will not be?
So the voltage between the, just right where the capacitor is stays the same.
Okay, so the voltage of the capacitor. Okay, so
Yep,
I'm
that,
guessing it's different.
and it could be different at the node. Maybe I'll label this VX. So this node VX
Oh, because, okay.
is going to be different there. Because you have the switch there and then all of a sudden there's not one and your circuit's different.
Okay.
So that node voltage at VX will change.
So it depends if I'm looking at a capacitor or inductor to see whether or not.
It's to VX.
Okay.
Okay, maybe I'll label it that way. All right, other questions?
So for the current going across the capacitor, it's just for a brief moment, that line is 2 milliamps.
Yes.
But if it's a little bit longer, it will slowly transition. Little bit.
It will transition to 0 because of the final circuit. Right?
Yeah.
So it will start off at 2 milli and then go to 0. And then we don't know quite the response in between there. For the capacitor, you're starting off with 0.2 milli. And then you need to find what that final value will be. That's the next step. Okay. All right. So for this next step in the final, so now we have our initial value for IC0, VC0. Now we need VC infinity. So inductor, yes.
So for this, right? Like 0, 0 plus and.
Yep.
Infinity,
So,
it's three.
Well, it would be 4 circuits, one for 0 minus, one for 0 plus, one for infinity, and then one for RTH at infinity. So 4 redrawings. Okay. So is everybody with me so far on the initial part? Initial values, everybody that good, or any other questions with that one? There's no, okay, there's a question online. Okay. How's their current going through the capacitor if it acts like an open in the circuit? Okay, I just answered that one. Okay, good. All right, so final circuit. We have the inductor acts as a wire again because now it's sat there again for a long time. So no more change. Capacitor becomes an open. And again, we see that this is 0 flowing through there because it's a floating wire. VC infinity is going to be here, or VC final, whatever you want to call it. And hopefully you can see that these are, there's ground at the bottom. And so again, the green wire, I'll call it VX2. So again, love my node voltage. So minus 4 milli plus VX2 minus 0 over 0.1 equals 0. And VX2 in this case is the same as VC at infinity. And that gives me 0.4 millivolts. So that would be my final value. Everybody follow me on that one? Yeah, okay. So now I need to go back and find A1, A2, and to do that, I need to find also S1 and S2. So S1 is going to be a minus alpha, which was 6.2. 6.2 squared minus 6 squared minus 6.2 minus the square root of 6.2 squared minus 6 squared. So S1 is a minus 4.64 and S2 is minus 7.76. So A1, 1 over C, which was 1 over 1.8. And IC0 is this initial value of 2 milli. S2 minus and minus 7.76. And then VC0 was 0.2 millivolts, and the final is 0.4 millivolts. And then over S2 minus S1, so minus 4.64, minus that minus 7.76. Yeah.
It's 1 over C, wouldn't it be 1.8?
Yes, thank you. 1 over 1.18. So I did redraw that wrong. Okay, so this gives me a value of A1 is 0.66 milli. And A2, I do the same thing as far as plugging it in. So 1 over 1.1.8. My heavens. And so this gives a value of A2 as minus 0.86 millivolts. And now I can write the full equation. So VC of T is going to be 0.4 plus 0.66 e to the minus 4.64 t minus 0.86 e to the minus 7.76 t. That's in millivolts. So if I wanted to find IC of T, what do I do? You have to integrate that. I'm going to leave that as an exercise. And again, you can use online tools to help you do that derivation too. Okay. So yeah, you integrate it or you differentiate it. Oh,
Okay.
yeah, to find, so it's C dV dt. So you take the differential of it, differentiate it. Yeah, not integrate. Sorry. Differentiate it. I said it wrong. All right, questions? You guys following this? Okay, barbecue. So we are going to leave early and you guys can go grab some food. So it's just right outside, outside the lobby. So upstairs in the, this is it. Go eat some barbecue. So upstairs outside of the Warnock Engineering Building on the patio there. Sorry, you guys will miss it that are online. See you guys.